1, right? And then, of course, that means that R3 minus R negative 3. Now it's non-zero. And so if I have 199, and now I'm comparing R3 and R negative 3, this is 1 and this is 0. So these two things are approximately equal, but that's not true for step 3, right? So you can't forget that this is only an approximation. You can't then rearrange this and say, okay, well that means that the rate is equal to 0 and then the net rate of the total reaction is also 0. Yeah?
What is a tolerable percent difference for it to be approximately equal?
Depends. I mean,
Is it like on the same order of magnitude, or is it like, you know, is it 50%? It's like a ballpark.
I mean, anytime, you know, if we're going to derive the equation without making this assumption, and it's nasty, or we've actually done this in the past just for a non-surface catalyzed reaction, and you might remember that you get this difference in rate constants. And if that difference in rate constants in the denominator is large enough, then you have a quasi-equilibrated step. You know, this is one of the test questions. Reintroducing that other parameter will give you a more accurate value, but how accurate, it depends on the rate constants and things like that. Certainly that, I would consider that to be quasi-equilibrated. The fact that the reactions occurred 199 times, but on a net sense, it's only occurred once. That's a pretty good, you know, fraction. That's 1 is the net reaction over 199. That's how many times it's gone back and forth. So that's a pretty small fraction. But I mean, above 10%, I would, if that number gets above 10%, I might not call it quasi-equilibrated anymore. But that's just an arbitrary distinction. What it really means is if you still use that assumption, your rates are going to be wrong. How wrong can you tolerate is up to you. Okay, so even though we do set this equal to 0, and that's how we solve for the equilibrium constant. So that's another way to solve for the equilibrium constant, so we'll do that real quick. So you get A1 is the forward rate, right, times A star, or excuse me, star, minus K negative 1 times A star. And of course, if I rearrange this, what do you get? You get K1 over K minus 1 is equal to A star times concentration of star, A times concentration of vacant sites over the concentration of adsorbed sites. And of course, that's equal to the equilibrium constant.
Shouldn't it be the inverse?
Yes. But again, don't let this confuse you into thinking that the net rate is somehow 0. It's not. It's just that these two things are approximately equal. So this is approximately equal to 0, which means it's approximately equal to, that the equilibrium constant is approximately equal to this ratio of concentrations. Okay, so let's do that for step 2 as well. And we'll go ahead and assume that this third step is quasi-equilibrated, because I forgot that I made this reversible, so we want to assume that as well. Okay, so step 2 means I can rearrange this and put B star is equal to K, now 2, concentration of B in the gas phase, and then star. And notice that we wrote step 4 as a desorption reaction. So if we're going to leave it as written, we have to put 1 over K4 here, because I'm still writing it in terms of C star is equal to. Everybody see that?
So 4 is also quasi-equilibrium?
Yeah. Oh, yeah, sorry, I didn't mean to put 3. Yeah, it wouldn't make any sense. 3 is the rate determining step. It's not quasi-equilibrium. Again, we only really need that because right now this step is reversible. If we make the assumption that it's irreversible, step 4 is inconsequential. And we will make that assumption, but we haven't yet, so we need to find something for C star to put into here. So within this assumption, we get that the net rate of the third reaction small k1, 3, sorry, times, now A star is this. And then B star, right, which is K2 minus K negative 3 times C star and then finally times another star. So let's simplify that a little bit, and you get K3 times K1. Again, this is a big K, big K2, concentration of A and B in the gas, concentration of sites squared, minus K negative 3. So we've related the rate of our reaction. Now we've essentially eliminated using the assumptions of quasi-equilibrated adsorption and desorption steps. We've eliminated the concentrations of our adsorbed species. Why do we care to do that? Exactly. Those are very difficult to measure compared to a gas phase pressure, which you can pretty easily measure, or more likely you're just setting what the pressure is, right? You control the reaction conditions. So you know what these gas phase pressures are. You don't know what the concentration of their adsorbed species are very easily. So I'll put one more simplification in there just to match what the book has.
You can measure the star because it's a catalyst property.
Oh, we're going to talk about that. For now, don't worry about it, but we're about to bring that back into it. So yeah, I just wanted to put, this is what the book shows, is they usually show K3 out front, and then we're going to put a prime there, and then what they have here is A star. No, sorry, they haven't put in the, yeah. I think they bring the stars out front. But they don't like to show reverse rate constants for some reason. They always bring the forward rate constant out, and then they put the equilibrium constant here. So that's what their version looks like. It's the same thing here. You're just factoring out K minus 3. Or you're factoring it in, I guess. You're factoring in a K3. So you get K3 over K minus 3. So now, how do we deal with these stars? No, they're not. We can't do PSSA on vacant sites.
If you're doing something about the material.
Yeah, we have to relate this back to something about the material. So let's do a total site balance. So what's on the surface?
Stars.
Empty sites. And so now we can use that this site balance in order to relate the concentration of empty sites to the concentration of first total sites as well as the concentration of species A, B, and C on the surface. And as a reminder, let's leave star as star. We already have an expression for this, right? So what is A star? It's nothing but K1 times the gas phase concentration times the concentration of sites. All right? K2. And then again, because we wrote step 4 as a desorption, it's going to be K4 to the negative 1.
What'd you say L was?
Say that again.
What'd you say L was?
That's the concentration, that's the site balance. That's the total number of sites. So that is a property of the catalyst. All right, so we can simplify this. You get L equal to star times 1 plus K1 and so now what is star squared equal to?